So welcome back. Okay, last class we discussed, and we've already been through all this. First law of thermodynamics. You can add thermal energy by doing work or by adding heat. Like, those make sense. Looking at it, we also get for ourselves then a second law of thermodynamics. And we'll jump in here. And what color is thermodynamics?
Orange.
Sure. Orange. Can you guys see orange?
Yeah.
Okay. Orange it is. So here we go. The second law of thermodynamics. Do you guys, I'm just going to do random talk and stuff while we get there. Do you guys, all right, second law of thermodynamics. We already know this one. If I have energy, I have two regions in space. Don't care how big they are, it doesn't matter. One is really high energy, whether it's thermal or it doesn't matter what sort of energy. Really high energy. And another region is really low energy. The universe wants to balance itself out. Which direction does the energy flow?
Hot to low.
High to low, hot to cold, every time. Every time. Now, that is the second law, and we have hit that so many different times. Energy always, always, always flows from high energy to low energy. Energy always moves. From high to low. And I'm going to say high energy to low energy. Always. Okay. From hot to cold. High to low. Yes to no, if you're Katy Perry, maybe. That is the second law of thermodynamics. It is always the case. Now, the cool thing about this is eventually, given enough time, our universe will be gone. It's going to take a really, 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 really long time. But the universe wants, and whether it really wants it, I don't think it does. I don't think the universe is conscious, but who am I but a small part of the universe? A weird idea. Eventually, everything will have the exact same energy in it, which means everything is just going to be uniform all throughout the entire universe. Now, if you look, and we're not in astronomy, so I'll just stop there. Okay. Cool. The universe wants stability, and I would be careful with saying wants. Now, when we deal with thermal energy, and obviously it's a pretty important part of our lives, especially because we live somewhere cool and our bodies need to be able to stay warm to run. The big deal that we look at as human beings is, one, how do we make sure that we're warm? And we talked about insulation and all that throughout that process, so that's a pretty good way to do it. We talked about using different energy sources to produce heat, right? What's the difference between passive and active solar energy or solar heating? So I'm going to do a quick check real quick. I'm going to give you guys a minute to check or to talk. But passive versus active solar is one thing that I want you to address, because there is a difference to these. And then the second one that I want you to address is, how does radiator work? Not in a car, but radiator as in for heating. These are the two questions. Without checking your notes, ideally I want you to check this. And I'm going to see if I can't find a video that I saw yesterday that was exactly covering this stuff. Cool. So, check it out. You get 60 seconds. I want you and your neighbors, passive versus active solar heating, and how does a radiator work? Basic ideas. Go.
Okay.
All right. So, we have those ideas knocked out. So, we've looked at thermal energy being used in a variety of ways. How did you get to school today? Car. Anybody in town or any of you guys get to school today with an electric vehicle?
Yes.
Really, you did?
No.
Oh, you got me good. Max could have, right? Okay. So as we look at this, one of the big things that we do with thermal energy, and our focus today is going through the process of converting thermal energy into movement or into mechanical energy. Okay, now these, depending on how interested people seem to be, we can go either really in depth or just kind of touch on them. Looking at it right off the bat, making mechanical energy into thermal energy, super easy. We can do it with our hands just by doing this, right? That's our first law of thermodynamics. We do work, we can add heat to a system. The other direction can be a little bit more complex, and it's been around for quite some time in reality, way longer than you guys probably think about. So, we can do the opposite. However, this is not very efficient, just so we're on the same page. Right off the bat, the first of these, we're going to talk about what is called a heat engine. A heat engine. It could be. As long as you're using heat to move it into like something that powers a vehicle, absolutely. So we use petroleum products primarily today, right? Like that's how we burn gasoline or diesel to power our vehicles. Trains, what do trains use?
Coal.
Not primarily, not anymore. They move a lot of coal, but old school locomotion was like somebody would be in there literally shoveling coal into a furnace to do this. Now they use diesel for the most part. Diesel or propane. I was talking with somebody yesterday, and apparently Matson is updating their fleet to run off of propane instead of petroleum products. Let me scratch that. Propane is a petroleum product. Propane instead of diesel because it's more efficient.
How do they extract propane? Like, what is that? Like,
It's a byproduct of collecting natural gas.
What's the difference between propane, butane?
So anything that ends with ane is a hydrocarbon. So propane, butane, like all those that you're thinking of, they are all out of the ground from fossil fuels. Like old algae died and then rotted and became oil. Is essentially what happens. Okay, anyway, heat engines. These guys, super easy to deal with. We're gonna say chemical energy to heat energy into mechanical. Now, there are variations of these that have been around for a long, long time. Vehicles as we know them that run off of gasoline or diesel, whatever it is, how long have cars run off gasoline? Couple hundred years. Think so?
Right?
How far back in time could I go and still buy a car? Money's not an issue.
18th century?
18.
So
1700s?
later end of the 1800s would be when it is. Henry Ford was a big revolutionary guy that came through and said, hey, let's make this process a little bit easier. Cool. What about before that? Like trains existed before that. What did trains run on?
Coal.
So I like both those answers. They're both right. We used coal to heat stuff like water to produce steam to turn stuff. Okay, that has been around for how long? How long has steam energy been like known and used?
1700s?
So like in wide scale application, probably around the 1700s, the industrial area. Oh my gosh, era. All right, cool. I'm gonna start scratching records, by the way. Anybody know what I mean?
Yeah.
Okay, I didn't. All right, I'm not really probably. Anyway, turns out crazy. There were steam engines like thousands of years ago. Greek philosophers and scientists at the time were able to make steam engines, but they used it to not make motion. They used it to open a door, and it was just as like a magic trick that kind of disappeared. Yeah, crazy. Anyway, looking at these, the most common that we deal with today in this is our internal combustion. What's an internal combustion engine?
2JZ.
What?
JZ engine.
Okay, so
6.
you are giving me car stuff that I don't know about, but I believe you. I assume it's car stuff. Okay, internal combustion, your vehicles. We all know they run on gasoline, right? How many of you have a basic understanding of how an engine works? Okay, give me a rundown. You can even piece it together with everybody. What happens?
Okay, so camshafts, maybe little nubs everywhere.
Okay, so we have a camshaft. So it's here, and then it has a big gear on the end.
Do you want us to draw that?
You don't have to. We'll talk about it. So here's a camshaft that's going to have some gears that turn your drive shaft, right?
So yeah, some cylinders.
Okay. Oh, there's cylinders on here. What's the cylinder look like?
It's like a thick hammer. I don't know, like a hammer, like a cylinder on a stick, basically.
So I have this thing, and it's in a tube, right?
Do you want to go to V or inline?
We're just gonna do one cylinder engine.
All right.
Okay.
And then the shaft will rotate.
Okay. So
And-
why does the shaft rotate?
I don't know, to burn some engine.
Not why. How? Like what spins
How?
the shaft?
It just turns. It just,
Oh, isn't it
Just
an
turn.
explosion?
I think you're backward.
am I backwards?
You're backward. Okay. I'm gonna have you guys draw this one really quick. It's gonna be easy. we're going to draw a cylinder, and we're just going to draw a single cylinder. I don't care about the camshaft and the drive shaft and all that. Okay, if we talk about a cylinder, it's a piece of metal that has a little spinning like bevel in here, and it sits inside of a larger little cylinder piece. So here's our cylinder right here, and we have a way to get fuel in, and then a way to get stuff out. Now, what winds up happening as this moves is we use a battery to first start this process. We fill this little guy with fuel, and this is my cylinder filled with fuel. Okay, the battery then for the very first time pushes this piston right here, this solid piece of metal, straight up, and it compresses it all. Okay, once you have a little area with a bunch of compressed gas in it, gasoline in this case, there's a plug up here that does something. The what plug?
Spark plug.
The spark plug, because if you have a bunch of highly pressurized gasoline inside of a cylinder and you introduce a spark, what happens?
Explodes.
It explodes in a very controlled way. When it explodes, it pushes this piston which way?
Down.
Down, which in turn raises another piston, so forth and so on, and this is how your internal combustion motors work. Sonny, you were right that all this motion does wind up, you were backward on it, but that's okay. All this motion that happens here connects to your drive shaft, which turns everything else. It's not the other way around. This motion is changed via gears and like really fancy, honestly, hardcore engineering to make your drive shaft turn. Cool. So, for this, we're just going to make this process as simple as possible. Fuel pumped into cylinder. Okay, and then the battery is often responsible for this first one, or back in the day you used to hand crank it, or if you drive a manual car you start pushing it and then you push it into gear and it makes this turn as well, the way that you were thinking, Sonny. Cool. Then what happens? We got a bunch of fuel in here.
Spark plug.
The piston, well before that,
Oh, piston.
the piston, and do you guys know what I'm talking about with the piston? Who does not have any idea what I'm talking about with a piston? You may. So just in case you haven't, we'll look at a GIF of it here in a second. Drum roll, please. Hey, cool. All right. So piston compresses gas. Compresses gas. Then what?
Spark plug. Right?
Spark plug sparks or fires. Whoa, plug ignites gas. Okay. What happens with the piston when that spark plug fires?
Going down.
Push it down.
Okay, piston push down. Piston down. And then check it out. We're back to here. Now, there are a bunch of moving parts that all these work in order, which if you've ever heard anybody talk about a cylinder's not firing, there's an issue there because you need that motion to keep like compounding as we go. If you've never seen it, you can make some really cool different types, but we'll just look, and I'm just going to Google this. Let's see, GIF of internal combustion engine. Cool. All right. Wikimedia, is it blocked? Will it play a GIF here, you think?
Got a gift?
Oh, you guys are wrong.
What?
Check it out. Here they go. Piston up, gas pushed in, spark, boom, pushes it down. Exhaust goes out the other side. Okay, this process just repeats and all this motion keeps compounding. Okay, easy.
Wait,
Yo,
cars usually have a few of those, right?
at least 4.
What happens if one stops working?
Your timing gets off and your car runs like garbage. Yep, really common. Other question, I think, or just a stretch, I couldn't tell. Cool. All right, so with these, whether it's small differences if you're with diesel, diesels don't use spark plugs. They use glow plugs instead. Diesel is unique in the way that it burns, but that's not our focus. All right, I'm going to make a quick comment here. Efficiency of these guys. For this, we are getting better and better and better about making vehicles more efficient with regard to how much fuel do they waste. What do we put in vehicles to make things run smoothly to reduce friction?
Yes.
Well, gas is what we burn.
Oh, oil.
You put oil in, right? We use oil everywhere. Even if we have oil, there is still friction. We want to minimize it to the best possible ability, but there's still going to be friction, which means your engine gets a lot of the energy that doesn't go directly to the tires. If I started my car and let it run for 20 minutes, or any car, Would you go out and put your hand on the engine block?
No.
Why?
Because I'll burn myself.
It is hotter than heck, right? The fact that it is super duper hot means a lot of that energy that could have gone to your tires must have gone to heating up that big metal engine block. Okay, there is loss that happens here. Depending on this, there are huge issues with it. We're just going to say not very efficient. Not very, which is subjective, but we obviously lose a lot of our energy to heating up that engine block. Not very efficient, ... getting better. We are getting more and more efficient as, but getting better, weird, sorry. We're getting better as the price of fuel and those sorts of things become more of the primary driver of what people decide to purchase. Yes, sir.
Maybe it's a rest.
Yes, that's fine. Okay. Now, here's a weird idea that's going to seem like we are just taking a big leap here. We looked at heat engines. And just think about what's going on here. We are taking thermal energy and we're making it move stuff, which nothing too crazy about that. What direction does energy always move?
Hot to cool.
Down.
Low.
High to low.
High to low, hot to cold. Is there ever any situation where we need to make stuff colder?
Yes.
Where?
PCs.
So a PC is a good example of it. Not where my mind went, but for sure. If you wanted to keep, like, I don't know, a gallon of milk cold, what do you do with it? You put it in the fridge, and we plug in our fridge, and it makes stuff colder? How do we, so the refrigerant,
Freon.
so you're right, we do use a refrigerant. Let's talk about that, though,
Toxic.
because it's a weird idea. We can use electricity to make heat, right? We can also use electricity to get rid of heat. So we should talk at least briefly about a refrigerator.
In like the 70s, they had this stuff that made a hole in the engine.
For real, we did. That
I know,
seems like
you-
I'm
you
having a little
told
bit of deja vu, but yeah.
Wait, what?
Okay. The ozone layer was destroyed by refrigerants. Okay. How hardcore do you guys want to talk about refrigerators?
Super hardcore.
Hardcore.
Like, so crazy that our brains will explode.
I probably can't go that crazy, but we can get a guest HVAC speaker in here if you guys really want to. I can find somebody that works with reefer stuff to come in and talk about it. Let's go basics first. Okay. How much picture do you want?
Picture.
Because we're going to need some picture.
Dose.
Not too much.
What?
Okay.
One drug.
Okay, so in interest of saving a little bit of time, how many of you guys like pictures in your notes to make sense of stuff?
Yeah.
Sometimes.
Okay, I'm gonna copy and paste this because this is my picture.
Whoa.
Okay, there's my refrigerator that I've drawn. Okay, and I'm just gonna use this. I'll just copy and paste it. If anybody wants to draw it, you're welcome to, but I'm gonna talk about it for a bit just as we go. So we have a lovely refrigerator here. Now this is like a basic kind of oversimplified one, but let's talk about what's going on. And I'm trying to be. Do you take most notes in my class?
Yeah.
Every single note.
But like you write more in my class than any others.
Yeah.
No. Math.
No. What?
Interesting.
This class is
Okay,
definitely more.
so here's my suggestion.
This class is 10 times.
You can write as much as you want. Like I'm never going to tell you you have to write. You have to. Okay, I lied. I'm going to tell you have to write something. You should be writing something. But it's entirely up to you how much you want to go with, right? Okay, we're going to talk about this. We have a fancy fluid in here, depending on what it is. It could be a Freon gas or liquid, depending on the situation. But we have a refrigerant, a coolant in here that's better than water. Now, what happens with stuff like if I were to take steam, and you may not know this, but if I had steam, for example, and I had a bunch of steam in a little area and I compressed it way down, what do you think happens with it?
It expands and goes somewhere else.
So it can't expand. Like, let's think about this. And this is an interesting thought. Again, you don't have to draw it. Let's say I had a bunch of gas in here. Okay, there's this many gas particles. Okay, and they're a gas. They're far apart, right? Particle model. And then I have a plunger on top. Not like a toilet plunger, but something I can push down. And I start moving this down. So that in the next picture, I have just this much space now with that same amount of particles. And do they have to be closer together now?
Yes.
Eventually, they're going to get so close together that they can't be a gas anymore. They're going to turn into a what?
Solid.
So, eventually, sure, but you skipped a step. It goes to liquid first. Now, this idea, we can compress a gas to make it a liquid, and if we expand it, it goes back to a gas. Like, that happens. Are we okay with that? Just like, you say no. Gosh, I just want to go to YouTube every time because there's so many cool ways to visualize this. We're just going to accept it. You push on a gas hard enough, it can turn to a liquid. Okay, so check it out. We have,
Isn't a gas already a liquid though?
no, different states of matter. You may be confusing it with fluid, but remember fluid isn't necessarily liquid.
It's steam.
Steam's a gas. When you feel it as wet, you're feeling it condense back down into a liquid on your hand. Okay, so check it out. I'm just going to talk about this one. Up to you how much you write. We have a gas that is pushed in here, and it starts to expand. So it's a little bit more chill than that. We have a hot fridge right now. So a box with a bunch of heat in it. If I have cold liquid, because it's been made into a gas, and there's properties here with the chemistry that we're not going to go into, but I have really cold stuff running through here. This cold isn't going to spread from this pipe into here. It doesn't work that way, right? Because energy goes from hot to cold. I can't push cold air out of here. Now, what I can do though is if this is really cold, if the air inside is warm, will this start absorbing that energy? Yeah, I can go from hot to cold. I can have the air here start to lose energy as it gets added to this liquid that's going through. Okay, as I come in, I'm really, really cold, and as it has more time to absorb heat from the air around it, it starts to get warmer and warmer, right? Okay, I then have a warmer gas. I wouldn't say hot necessarily, but it's significantly warmer because it's collected all the thermal energy from inside the box. It then comes back through, it compresses back down, and it runs through a specific place with a fan where it can now blow all that thermal energy that's radiating off of it out from your fridge. If you guys ever stood in front of your fridge and on the bottom, if you ever seen the piece that falls off, there's like those little metal coils and you might feel air coming out of it sometimes.
Oh, yeah.
What's going on is it's blowing a fan to get rid of all that extra heat. It then condenses back down, and then it runs back through and does the same thing. As long as whatever's pumping through here is colder than the air inside, these coils, these pipes, are going to keep absorbing energy from inside. We don't add cold to stuff, we take away hot, and it works through this process. That's the basics of refrigeration. Now, as we go through here, I'm okay to not write anymore, if you guys are.
Yep.
Okay, sweet. What about an air conditioner?
Same concept.
It's just cooling down air.
It's cooling, so this is also cooling down air though, right?
No, but that either, no, but
Does it propel
does air conditioner
air
use
out?
air,
Or cold air?
or does it use the same concept? Like, you know,
So it depends on your type of air conditioner, in all honesty.
mine's on the wall, like up top.
Yep, so there is coolant in it. It is essentially the same process. You're absolutely right. I just want to make sure that we could hit on it.
Oh.
Okay, very specifically, similar process runs through. It's a bit more obviously centered to making air blow out cold rather than blowing out hot air, which is what this guy does because it takes the heat out, but same idea. Cool. All right, here's the deal. I'm going to leave it up to you guys. We have 16 minutes left in class. For today, we just finished the section. We're going to look at homework 5.3, which you guys will find waiting for you on page 134. You get the privilege of problems 16 through 22. And let me see if I need to take out some of those because we went over refrigerant really fast. Okay. Yeah, just to show you guys like how crazy, like I went over this much faster. Here's a picture from your book that they use with fridges.
Oh.
Oh.
But it's the same idea. I see pipes running through, a liquid coolant that absorbs all the warm energy, gets warmer as it goes through, and then it gets rid of it. Okay, same idea. Here's your choice though. We have 15 minutes. You guys think piecewise function is going to be on your final algebra exam?
Yeah.
It is.
Definitely.
He told us it will be.
It's everything we've been
Okay.
learning since the last.
Do you want to graph one piecewise function first,
Yeah.
and then we'll commit?
Yeah.
All right, and you guys graph linear functions, is that true?
Yeah.
Yeah, I'm not sure.
Like everything you do is a straight line.
Yes.
Yeah.
Okay, MX plus B?
We haven't
Yeah.
done.
Slope.
Okay, so here's the plan for this class then, just so you know, on Wednesday when we meet again, we will have time to look and review for the test that'll happen on Thursday. Cool. All right,